There are moments in astronomy when a discovery does more than add another object to a catalogue. Some discoveries change the way scientists think about what is possible, and this is one of those moments. The James Webb Space Telescope has directly detected a remarkably faint planet around a young, nearby star, giving astronomers an unprecedented look at a world that was previously hidden inside its star system. For most of the history of exoplanet science, finding another planet meant finding evidence that something was there without actually seeing the planet itself. Astronomers watched stars dim when planets crossed in front of them, measured tiny movements caused by a planet's gravity, and studied subtle changes in starlight. These techniques have revealed thousands of worlds, but the planets themselves usually remained invisible. Now Webb has opened another door. Using its mid-infrared instrument, or MIRI, astronomers detected a faint infrared source in the debris disk surrounding a young star called TWA7. The object, known as TWA7b, is best explained as a cold sub-Jupiter mass planet located roughly 52 astronomical units from its star, and the discovery was published in Nature in June 2025. That distance immediately makes the discovery fascinating. 52 astronomical units means TWA7b is orbiting its star at roughly 52 times the average distance between Earth and the Sun. If you placed it in our own solar system at a similar distance, it would be far beyond Neptune, deep inside the cold outer regions where sunlight becomes dramatically weaker than it is here on Earth. But the distance from its star is only part of the story. TWA7 itself is extremely young, estimated to be about 6.4 million years old, while our Sun is approximately 4.6 billion years old. In cosmic terms, TWA7 is still practically a newborn star, surrounded by a debris disk containing material left behind from the violent and complicated process of planetary formation. That debris disk is what made this target so interesting in the first place. Astronomers had already observed a striking structure around TWA7, including multiple rings and gaps extending outward from the star. Those patterns are important because planets can gravitationally interact with the smaller bodies surrounding their stars, pushing material away and shaping the disk into rings, gaps, and other structures. For years, however, there was a problem. Scientists could see the structure, but they could not see the planet that might be responsible for creating it. It was like seeing a trail through fresh snow and knowing that something must have passed through, but never actually catching sight of whatever made the tracks. That is where Webb changed the situation. The telescope observed TWA7 in June 2024 using MIRI's coronagraphic capabilities at a wavelength centered around 11.3 micrometers. After carefully processing the observations and suppressing the overwhelming light from the star, researchers found a faint source approximately 1.5 arcseconds away from TWA7. The challenge may be easier to understand if you imagine trying to photograph a tiny candle sitting directly beside a stadium floodlight. The candle is producing light, but the floodlight is so much brighter that the weaker signal disappears inside the glare. A planet orbiting a star creates essentially the same problem, except the difference in brightness and the distances involved make the astronomical version vastly more difficult. A coronagraph helps solve that problem by suppressing the light coming directly from the star. Webb's MIRI instrument contains coronagraphic systems designed to block and manipulate starlight so that faint objects nearby can become detectable. This does not make the star disappear completely, but it dramatically reduces the glare that would otherwise overwhelm the planet's signal. Even after the coronagraph does its work, the observation is far from finished. Tiny amounts of residual starlight remain in the data, and the telescope itself introduces patterns and artifacts that have to be understood. Scientists therefore use reference observations and sophisticated processing techniques to remove unwanted light while preserving genuine sources that could represent planets. This is one reason direct imaging is so difficult. Finding a faint spot is not enough. Researchers have to determine whether that spot is actually connected to the star or whether it is simply a background object that happens to appear in the same part of the sky. A distant galaxy, star, or other unrelated source can create exactly the kind of false signal scientists have to eliminate. The TWA7 team therefore examined the source carefully. The probability that the detected object was a background galaxy was estimated to be very low, while the source's position and infrared properties were consistent with a young, cold planet. Most importantly, its location lined up remarkably well with the structure of the surrounding debris disk. That alignment is one of the strongest reasons scientists interpret the object as TWA7b. The planet's estimated position is around 52 astronomical units from the star, close to one of the prominent structures in the disk. Models indicate that an object with approximately the estimated mass of TWA7b could naturally account for important features observed in that region. And this brings us to the number that makes this discovery so important. TWA7b is estimated to have a mass of around 0.3 times the mass of Jupiter, or roughly 100 times the mass of Earth. That places it firmly in the sub-Jupiter category, making it dramatically less massive than most planets that had previously been directly imaged. That may not sound revolutionary until you understand how difficult it is to directly image smaller planets. Earlier directly imaged exoplanets were generally much more massive and therefore much brighter in the infrared. TWA7b represents a major step downward in mass, showing that Webb can push direct imaging into a regime that previous instruments struggled to reach. The Nature study reports that TWA7b is at least 10 times less massive than exoplanets directly imaged before it. Even more remarkably, the researchers estimate that under favorable conditions, Webb could potentially detect planets in the range of roughly 25 to 30 Earth masses at similar separations from TWA7. That does not mean Webb has photographed a 25 Earth mass planet. It means the sensitivity demonstrated by this observation suggests that even smaller worlds may be within reach if they are located in sufficiently favorable positions and have the right physical properties. And that is where the discovery becomes much larger than TWA7b itself. Because the real breakthrough is not simply that astronomers found one more planet. It is that a space telescope has demonstrated a powerful new capability for directly studying relatively low-mass planets far from their host stars. TWA7b is also interesting because it is cold. The researchers estimate an effective temperature around 320 Kelvin, or roughly 47 degrees Celsius, although this is the planet's effective temperature, rather than the kind of surface temperature we might associate with a rocky world. The planet is a young giant, still carrying heat from its formation, and its atmosphere could become an important laboratory for studying young planetary systems. It is important to understand that TWA7b is not another Earth. There is no evidence that this is a habitable rocky planet, and its estimated mass strongly indicates that it is a giant world rather than a terrestrial one. It is also located extremely far from its star compared with Earth's distance from the Sun. So why should anyone care about a cold, gas-rich planet so far from its star? Because TWA7b may be showing us how planetary systems are built. Our own solar system contains enormous planets surrounded by smaller bodies, rings, moons, asteroids, and icy objects. Scientists have long suspected that planets influence the architecture of their surroundings. Jupiter, Saturn, Uranus, and Neptune have all shaped the populations of smaller objects around them through gravity over billions of years. When astronomers look at young stars, they often see disks containing dust and debris arranged into surprisingly complex patterns. Rings appear. Gaps form, narrow structures develop, material becomes concentrated in some regions and depleted in others. One explanation is that planets are doing the sculpting. But until now, there has been a major observational problem. Astronomers could identify the fingerprints of possible planets without necessarily seeing the planets themselves. TWA7b changes that equation. Here we have a faint planetary candidate located directly within a structured debris disk, with its estimated mass and orbital position providing a plausible explanation for the disk's architecture. Instead of simply saying that a hidden planet might be responsible for a gap, scientists can now study a real planetary source sitting in the same environment and compare its properties with predictions from planetary disk models. This is incredibly valuable because planetary formation is still one of the great unfinished stories in astronomy. We know planets form from disks of material surrounding young stars, but the details are complicated. We do not know exactly how every planet reaches its final mass, how quickly giant planets form, how their orbits evolve, or how their gravitational influence reshapes the material around them. JWST is young enough to provide a snapshot of a planetary system during a very different stage from our own. Our solar system has had billions of years to settle into its current architecture. JWST is only a few million years old, meaning astronomers are effectively looking at a system still in its early development. It is like comparing a finished city with a construction site. Our solar system is the finished city, with its planets established and its debris mostly cleared or redistributed. JWST is still revealing the processes that can shape a planetary system while those processes are happening, and the debris disk itself is unusual. The Nature study describes JWST as a low-mass member of the young TW Hydrai Association with a disk seen almost pole-on. That orientation is particularly useful because it gives astronomers a relatively clean view of the disk's radial structure and makes it easier to investigate the relationship between the planet and the surrounding material. The star is also relatively close by astronomical standards, at about 34 parsecs, or roughly 111 light-years. That means the light Webb detected began its journey toward Earth more than a century ago. When the telescope observed JWST in 2024, it was receiving photons that had been traveling across interstellar space for roughly 111 years. Think about what was happening on Earth when that light began its journey. The world had not yet experienced the First World War. Powered flight was still in its infancy. Radio communication was developing. Modern computers did not exist. The technology that would eventually build the James Webb Space Telescope was unimaginable. And yet, light from that distant planetary system was already moving toward us. It crossed more than 100 light-years of space before entering the telescope's instruments. That is one of the strangest aspects of astronomy. Looking outward is also looking backward in time. Every telescope is, in a sense, a time machine because light requires time to travel from one place to another. When Webb observes TWA-7b, scientists are not seeing the planet exactly as it exists at this moment in 2026. They are seeing light that left the system roughly a century ago. The planet has continued orbiting its star during that time, while its ancient light was still traveling toward Earth. The same principle applies to every distant object in the universe. The farther away something is, the further back in time we see it. That means Webb is not simply taking pictures of space. It is collecting fragments of history carried to Earth by light. And TWA-7b gives us another example of how powerful that idea can be. The planet is so far away that no human spacecraft could realistically travel there with current technology. Even our fastest spacecraft would require an extraordinary amount of time to cross that distance. But photons can make the journey, and Webb can catch them. That is what a direct image ultimately represents. It is not a close-up photograph in the way we photograph planets in our own solar system. TWA-7b appears as an extremely faint point of infrared emission after the overwhelming stellar light has been suppressed and the data carefully processed. But that point is coming from a physical object orbiting another star. It is not an illustration. It is not an artist's reconstruction. It is observational evidence from a distant planetary system. And that distinction matters. For decades, exoplanet discoveries often produced strange situations where scientists could confidently say a planet existed but could not actually show people a direct image of it. The evidence came from gravitational effects, changes in brightness, or atmospheric signatures. Those techniques remain enormously important. In fact, most exoplanets are still discovered through indirect methods because direct imaging is extremely demanding. The transit method watches for tiny dips in starlight when a planet passes between Earth and its star. The radial velocity method looks for the tiny back-and-forth movement of a star caused by the gravitational pull of an orbiting planet. Both methods are extraordinarily powerful, but they each depend on geometry and favorable circumstances. A planet has to transit from our viewpoint for the transit method to work. A planet has to produce a measurable gravitational signal for radial velocity measurements. Direct imaging has a different advantage. If a planet is far enough from its star and bright enough relative to the remaining glare, astronomers can potentially detect it even when it does not pass directly in front of the star from our perspective. That opens a completely different population of worlds. And this is why the Webb observation matters for the future. The ultimate dream is not simply to photograph another giant planet. The long-term goal is to directly observe much smaller worlds, including planets that could resemble Earth in size and temperature, and that orbit within regions where liquid water might potentially exist. TWA-7b does not accomplish that goal, but it demonstrates technology and techniques that move the field closer to it. That is how astronomy advances. The first telescope does not immediately produce the final discovery. The first detector does not immediately find life. The first direct image of a sub-Jupiter world does not immediately reveal another Earth. Instead, each breakthrough expands what scientists believe can be measured. Then, the next generation pushes farther. This is exactly what happened with earlier generations of telescopes. Galileo's telescope did not show the universe in the detail we see today, but it changed what humans understood about the sky. The Hubble Space Telescope later transformed our view of galaxies, nebulae, star formation, and the early universe. Now, Webb is extending that revolution into infrared astronomy and directly into the study of distant planetary systems. The telescope's huge segmented mirror and infrared instruments allow it to detect incredibly faint sources that would be difficult or impossible to study with many earlier observatories. MIRI is particularly important in the TWA-7b discovery because the planet is young and still warm enough to emit detectable thermal infrared radiation. Webb was not simply relying on reflected starlight. It was detecting the planet's own thermal emission. That is a crucial advantage. A young planet can retain substantial heat from its formation, making it brighter in infrared wavelengths than an old planet of the same mass might be. That does not make direct imaging easy, but it gives astronomers a valuable window into young planetary systems. TWA-7b therefore becomes more than an image. It becomes a laboratory. Scientists can investigate its temperature, estimate its mass, examine possible atmospheric properties, and study how its presence relates to the surrounding debris disk. The researchers also point out that the planet is well suited for future direct spectroscopic investigations. Additional observations could help refine estimates of its temperature, metallicity, and atmospheric properties, which in turn could improve estimates of its true mass and help scientists understand how this young world formed. There is another fascinating detail hidden in the system. The researchers are interested in whether dust structures could be associated with the planet's orbit, potentially resembling the kinds of Trojan populations known from our own solar system. But this remains an area for further investigation rather than a confirmed discovery of an extrasolar Trojan cloud. Every time we build a better way to look, the universe gives us something new to explain. And somewhere beyond the edge of our solar system, another planet is already shining. Its light is traveling through the darkness right now. Perhaps that light has already begun its journey toward us. Perhaps another telescope, another scientist, another generation will eventually catch it. And when that happens, we may discover that TWA-7b was not the moment humanity finally saw another world. It was the moment humanity learned how to start looking